First up, our speaker is Nilesh and Binura. I would like to invite you to the stage, please. Nilesh and Binura, they are from Platformer. Welcome, Binura. We just wait for Nilesh to get here as well. So where are you located, Binura? Are you in Australia?
I'm in Sydney. Yeah.
Right.
Yep.
Sunny Sydney.
Yeah, it's getting sunnier.
Yeah.
And
hi, Nilesh. Welcome. So Nilesh and Binura is going to talk to us about managing application traffic in microservices. If you have any questions, please put it into the chat and we'll get to them at the end of the talk. Over to you guys.
Yep. Thanks, Julia. Let me just press on my
Thanks.
screen.
Yeah.
Can you see my screen, Nilesh?
Yeah, I can see a screen.
Cool.
Okay.
Yep. I better. Yep.
Okay, guys. We're going to talk about managing application traffic in microservices. So to give a quick intro, I'm Nilesh Janandana and I'm located in Colombo, Sri Lanka. I'm a principal architect at Platformer.
And I'm Binura. I'm here in Sydney, and I'm also an architect. And we basically work on some Kubernetes-related things at Platformer. So yeah.
So talking about the agenda, I'm going to be talking about how we handle traffic in Kubernetes, and then we are going to jump into how API gateways help us to solve some issues or challenges we have with Kubernetes. And then Binura will jump on and take you through with how to handle service meshes and deployment patterns with microservices. So moving on, first up is I just want to explain the difference between north-south versus east-west traffic. So basically, north-south, if you can see from the diagram, it's from the end user. When the end user requests traffic from your application, or requests talks to your APIs, that's going to be through firewall. It's going to go through a public load balancer, etc. So that we call north-south traffic. And then when your microservices are talking from one microservice to the next, we call that east-west. So moving on to the next slide. So there are few different strategies on how we route traffic in Kubernetes. The first one we call cluster IP. This is basically east-west traffic, which means that one microservice can talk to the other microservice through a cluster IP inside the Kubernetes cluster. Then there are two ways we can route traffic to Kubernetes, which is through north-south traffic, which is called node port and load balancer. So in this scenario, you can see in the middle diagram that we are routing traffic to Kubernetes through the virtual machines of Kubernetes through a specific port in the range of port 30,000 to 32,000. And we are routing our traffic through that to an internal service in Kubernetes and then load balancing into our pods. On the right side of the screen, you can see the load balance approach, where an external load balance is directly bound with a Kubernetes. If you move on to the next slide. If you move on to the next slide, Binura.
Yep.
Yeah. Okay.
Is the connection?
So.
Okay.
Okay. Can you go to the previous slide?
Yep.
Okay. Oh, I'm sorry. The next slide, please.
Oh. Is it lagging from my side?
I guess so. It's okay. So the next problem is basically next problem is the ingress, where we would have an ingress L7 balancer in front. So we would be sending traffic to an ingress. So the ingress would be doing reverse proxying in a Kubernetes native way through an ingress controller, and then we should be able to route traffic to whatever the services that we have. So in this diagram, you can see foo.mydomain.com would go to the first service, where domain.com/bar would go to the other service. So in ingress control, very basically, you can do rate limiting and all of that on the ingress controller itself as a whole, rather than we do it per service. And also ingress allows us to do path-based routing, and ingress allows us to do terminating TLS. So at the ingress level, we can set up, we can mount some secrets, the TLS secrets, and then we can set up SSL. So that's basically what ingress allows us to do. And at the bottom, I have included few ingress controllers, Nginx, Traffic, and a few others. So when it comes to the challenges, now in a scenario of microservices, we would have in an organization, we would have number of microservices, and there would come a time where we require the need for flexibility, which means that few users would be using different protocols. They could be using gRPC, HTTP2, HTTP 1.1, they would be using WebSocket, so all of that. And then most of these microservices, they might need to have different rate limiting, different mapping, and different deployment patterns. Some people might want rolling updates for their services. Some people might require other stuff, like they might want canary deployments or A/B testing and all of those things. And then you want to ensure stability of how you do a rolling update or how you update your microservices. How do you do if something fails? And how would you sort of like do retries? I mean, you can't really do those or integrate those inside the service itself. I mean, it doesn't make sense when you are working, when we're talking about thousands of microservices. And also tracing is a big component today, where tracing allows us to do to trace our microservices, see where things are lagging, see what the problems are. So all of that are big challenges when we are working with thousands of microservices in a complex domain. If you move on to the next one. So the solution for this is moving on from ingress is API gateways. So API gateways allow us to be flexible with our protocol support, which gives us, we can add a WebSocket, we can add gRPC, we can have HTTP2, we can do the HTTP2 promotion automatically. All of that can be automatically handled per service in a Kubernetes native way with API gateways. And again, path-based routing. So we can have one big domain called api.platformer.com or something, and then we can have path-based routing for different microservices we have in the system. And then again, API gateways support terminating TLS, where we can mount our SSL certificates and etc. into that. But if you look at the diagram, the first diagram, you can see that in a big application or in a monolithic application, you have rate limiting, retries, caching, circuit breaking, all of those things embedded in the application itself. So if we do all of this inside the application, our microservice, the size of the microservice grows bigger. So rather than that, what we can do on the right side of the image, if you can see, we have put authentication, tracing, retries, caching, rate limiting, all of that to be handled by the API gateway. And then simply our microservices can handle the API incoming requests and the business logic. So that way we can easily do our work without, then we wouldn't have, our developers won't have a problem of cross-referencing different libraries and all sort of things, where a centralized control plane can handle all of that. So other than that, additional features would be API gateways allow us to have one of the main things that I like is they allow us to have a document portal, which basically, if you have a Swagger spec or an Open API spec, it just automatically do the discovery, and you can search through the APIs and all of that, and you can very easily work with those. Moving on. So to understand the use case, let's just look at a case study. So imagine we have a distributed system of about having 25 plus microservices, and each of these microservices will be scaled dynamically according to the load. And you sort of need to audit all the incoming logs, incoming requests that are coming in, and then you have to validate through a custom auth and an RBAC service that you yourself have written. And all the requests need to be traced and monitored. Each microservice would have its own limits. So sort of like an authentication system would have 10,000 requests per second, whereas a lesser domain like a shipping or something would have 2,000 requests per second. And then you need to maintain SSL through Let's Encrypt, and then you need to automatically renew this stuff. And then you might be using different protocols like HTTP2, WebSockets, or gRPC, etc. So a solution for this using API gateways, as you can see from the diagram, the traffic would come into directly to the API gateway, and then through API into auth service, which is on the left side of the screen, and that can determine if that incoming request is a good request or a bad request, and can return 401 on the spot or give a bad request error. And then it can also store everything in an audit log, and then the API gateway can move forward to the next step, which is the host. So it's going to do routing according to the incoming host of the request, where basically in this host we can set up our TLS settings. You can just set up Let's Encrypt certificate, inject it, and then you can have there's this module called Cert Manager, which allows us to manage our Let's Encrypt certificates. So you can do that, and then we can manage that. Now the next part is that we would be differentiating the incoming requests according to the path. So basically api.platformer.com/service1 would route to service 1, and /service 2 would route to service 2. And you can see here in these two services that the first service we have HTTP, it supports HTTP 1.1, and then we have some sort of rate limit applied there. And whereas the service 2, we have gRPC support and rate limit, and also it has retries. So if something goes wrong with the pods, it sort of supports retries. And other than that, in addition to these things, we can very easily do caching on this layer itself. And there are so many other things that we can do to make our system better. So moving on to the next step, we can talk about circuit breaking, better deployment and all of that, combining with service meshes. So I'm going to let Binur take on the screen with service mesh. Thank you.
Yep. So the first question that you really need to ask yourself before you jump onto a service mesh is whether you really need it, right? If your API and your internal systems compose of maybe 5-6 services, perhaps, you really don't need a service mesh unless you have some of those requirements that need to be met for compliance reasons or something of that sort. But otherwise, you can run a stable, sustainable system without a service mesh. So it's important to always look back and see if you are over-engineering, because remember, we already have the overhead of having to manage the Kubernetes infrastructure, and now we are going ahead and adding another layer on top of it so that we can get a service mesh running. So it does give us a lot of features and a lot of power to control what happens within the application layer. But at the same time, we are introducing a lot of more maintenance and maintenance complexity in the long run. So it's always good to take a step back, start small, and maybe if you really get to a point where you do need to inject a service mesh, you can do it. So it's a good idea to keep in mind as you go along. So just to recap how a basic service mesh works, essentially in Kubernetes, once you run your applications in pods, what a service mesh that's based on something like, say, the Envoy proxy would do is it would inject a sidecar proxy into your pod. So in addition to your application container, your pod will now contain a small sidecar proxy that will do all the routing, the audits, the metrics, the logging, and all of those by connecting to a central service mesh control plane. So we'll look at what this enables us to do in terms of deployments first. So the most common type of deployment that you get with service meshes is the ability to do blue-green deployments. Sometimes called red-black. I think Netflix made that very popular. But essentially, what you're doing here is you have the first version of your application, let's just call it V1 and V2 for brevity. It's running, it's serving live traffic. And then you wait until all your V2 services, or at least all the dependents of V2, come alive and are marked healthy. And only after then do we shift our production or our live traffic to the new environment. Now, this is a little different to what you usually get with Kubernetes as standard, right? We know you get rolling updates and you can do zero-time downtime deployments, where Kubernetes basically waits for the new container to spin up, does a few health checks, and if it all passes, spins down the old container, and it serves the new traffic to the new container and then spins down the old container. So the problem with rolling updates is that in that sense, it doesn't really account for version incompatibilities between your services, right? Your services in most cases are dependent on each other. And no matter how much we tell ourselves that we are backwards compatible, there are times where you have to introduce something like a breaking change. And for example, here we have one producer and one consumer. The V1 consumer is basically dependent on the V1 producer. And we introduce a new version of our producer, but with a breaking API change. So with a rolling update, what would happen is Kubernetes would wait for V2 to come alive and try to shift the traffic to a V2 producer. And because there are certain incompatibilities between these two dependencies, our service will probably fail. So this is where blue-green deployments come in. So instead of just rolling out services one by one, you can wait for an entire set of dependencies to come alive and then shift your traffic. So in this case, it waits for consumer V2, which has the updated details to talk to the V2 producer, comes alive, and then shifts the traffic without creating a breaking connection. So that's blue-green deployment, and that basically leads us to what's called a canary release. So these are similar to blue-green deployments, and in fact, you can sort of combine these together, run them side by side, and do a lot of things. Essentially, where this comes from is back in the day, miners would release a small canary into a mine shaft just to make sure there aren't any toxic gases in the mine shaft. And I don't know why they picked a canary. Probably it's anybody's guess. Unlucky bird. But essentially, the metaphor basically directly applies to application deployments. So without completely shifting over our traffic into a new version, with a canary deployment, what a service mesh allows us to do is route a certain percentage of our traffic over to the new version. So in essence, it's very similar to A/B testing, but with A/B testing, what you do is you try to make sure your users like a new feature, right? You just try to see if something actually will work. But with canary releases, they usually are followed by a full-on release, maybe a blue-green deployment. but it's essentially to make sure that I have a change. I need to route traffic bit by bit to make sure everything works and everything is stable. And once that is confirmed, you can go ahead and do a full cutover. And then another popular deployment pattern you see with microservices is something called a shadow launch. So essentially, this is ideal for scenarios where you have a substantial amount of changes in your system and you've tested it, but you want to take extra precaution. So in this case, with a bit of configuration, what you can do is that from your load balancer or your API gateway, you can replicate that production traffic onto an isolated environment, which is basically your shadow replicas. So in that sense, your production environment would still continue to serve your production traffic, but at the same time, you can see how well the new changes perform in an isolated environment. But of course, this is a bit more work than the other two approaches, because there are some parts where you need to mock out certain integrations. For example, if it's like a payment system that's connected into another external API, you'll have to mock that out, or your users will be charged twice. So things to think about, but with service meshes, all of this becomes quite easy and quite possible. So something I forgot to mention during the deployments is that when you're doing things like canary releases and shadow launches, you need to have the metrics to produce actual usable information. If you don't have a way to measure how things are working, there's actually no point in going for a canary release or A/B test or a shadow launch, because you don't really see what's happening. So with most service mesh tools and frameworks that run on Kubernetes come pre-packaged with a set of tools for you to go about doing this. And in essence, we see a lot of moving parts and a lot can go wrong really fast. So having that information under a single pane of glass, things like success rates, failure rates, latencies, and all of this can really help you get all of your systems under control in an event of failure. And in speaking about failure, distributed tracing is pretty important. So unlike in a monolith, you could just do a stack trace or just use your login library to log out how long things took. You're now talking between multiple services, and you need to know if something is slowing down, you need to figure out where exactly it's slowing down. So for those reasons, there are multiple distributed tracing libraries available that, again, come pre-packed with service meshes. And you can easily trace your requests and figure out where your application is slowing down. And then that takes us to retries and circuit breakers. So as Nilesh mentioned, as with API gateways, you can shift some of these things that monolithic applications do into the service mesh. So your applications remain agnostic of the provider. So with the service mesh, network failure is always going to be around the corner, right? Congestion is there, latencies happen, and sometimes you might experience an entire blackout. So for these reasons, there are ways to make sure your application requests are retried from the service mesh. So if a request fails, your service mesh can go ahead and retry it until it works. And this takes us on to circuit breakers. So essentially, circuit breakers are there to ensure that downstream traffic doesn't, downstream clients are not affected by latencies in upstream clients, and upstream clients are not overwhelmed by downstream clients. So basically, it's a way to sort of manage network congestion or latencies in your applications. Essentially, it's pretty simple. All your traffic goes through a circuit breaker, and a circuit breaker has 3 states. So it's either open, where it's serving traffic, it's closed, where it's not serving traffic, and we'll get to half open. So essentially, once it's open, serving traffic, but if a service times out or fails, the circuit breaker closes. And once it closes, it waits for a set timeout before it retries. So when it does retry, that's called a half open state. And in this state, what the circuit breaker does is it tries to resend the request, and if it fails, it just goes back into a closed state and redoes the timeout. But if it succeeds, that means the congestion might be solved. It just re-enables the traffic to flow through your circuit breaker without interruption. So that brings us to the last part that we're going to talk about, which is mutual TLS. So essentially, this is probably the easiest way to secure traffic between your services, for example, inside a Kubernetes cluster. So essentially, with the service mesh framework that supports Envoy, you can have your sidecars verify each other's identity before they send traffic to each other. So they verify each other's identity using a root CA signed certificate, which is mounted onto both of them. And the service mesh basically takes care of rotating those certificates as well. And once that initial TLS handshake succeeds, it encrypts the data with a symmetric certificate and sends it. The server picks it up and decrypts it with another symmetric certificate. So this way, both components, services know who they are talking to. And if you have a large number of teams working on a single service mesh, it's a good idea to have mutual TLS just to make sure that you can control who's talking to who. So with that, that brings us to a closure on like basic service mesh principles and core concepts.
Thank you, Binura and Nilesh. That was great insights into service mesh and some Kubernetes. I think we've got some questions here from Phoebe. What are the architectures where if the gateway configuration changes frequently? What would you recommend as the best architecture?
Yeah, hi Phoebe. So when you run Kubernetes native API gateways such as Ambassador, there's another thing called WSO2 API Gateway and Glue and few others. So what they allow you to do is per service, you can create this. There's this thing called CRDs in Kubernetes, which allows us to sort of like define a subset of the configuration for whatever the service you want. And when you apply it to Kubernetes, it's just going to behind the scenes that API gateway controller would configuration the API gateway requires and just applies behind the scenes for you. So that's basically how Kubernetes API gateway and how we handle different config changes per service in Kubernetes. We don't have to manage all of them at one repository or one central place. We just have to have different CRD resources and then apply them there. And then Kubernetes and the native ingress native API gateway controller you are using should take care of it.
That's great.
Yeah.
I'm just curious myself. Binura, you mentioned that some service mesh may not be the right solution for everyone. So as a company, what do you think is the main criteria people should kind of look at before they adopt service mesh?
Yeah, I'd say you should always start small, especially if it's a greenfield project. So first, you got to decide if you really need a microservices architecture. So, we're really quick to jump on board the cloud native train and break our services down. But in essence, if it's doing a limited number of things and you really don't need to scale the components separately, you don't need to firstly go for a microservice architecture. And secondly, even if you are going for, it's not calling a microservice, maybe a macroservice, where you have like a couple of components, right? Maybe 5-10 services running independently of each other. At that point, you really need to look at whether you need the features that a service mesh gives you. So things like tracing, you can still achieve that without using a service mesh, right? There are libraries and other third-party plugins that you can plug in, and it'll do the job for you. But if you really need things like mutual TLS, network policies, just to control who's talking to who, at that point, you probably need a service mesh.
That's great.
Yeah.
That's great. Well, that's all the time we have. Thank you very much. That was a great talk.
Yep.
Thank you, guys, for your
Thank
time.
you.
Yeah, thanks.